everyone. Welcome to 11.6. We're going to talk about a type of probability called conditional probability. So you can probably deduce from the word conditional, there's conditions involved here. And the condition is that one of the events already occurred. So in the last section, we learned that when two events are dependent, so remember that means the occurrence of one event affects the probability of the second one, right? We calculated the probability of A and B by multiplying. And we were trying to determine the probability of B, but we assumed that A already occurred. So we calculated the probability of event B given event A. This is known as conditional probability. It's the probability of event E2, so that means the second event. Okay, that's all that means. Is occurring, given, so that word given is so important here. When you see that word given, that means it's conditional. Given that event E1, that just means the first event, has happened, or it will happen. Okay, the time relationship doesn't matter. And it's written like this. So we would read that as the probability of event E2. And then that vertical bar right there, that means given. Given E1 occurred. Okay, let's look at an example, and we're going to learn about a formula that we can use that will make things a little easier. One of the things we want to keep in mind is if event E2 already occurred, or E1 rather, already occurred, the sample space is going to be reduced. So this part right here reduces the sample space. So here's an example or two. So when one card is drawn from a standard 52 card deck, determine the probability that the card drawn is a king. Okay, so nothing unusual there. How many kings do I have in a standard 52 card deck? I've got 4. So the probability is just 4 over 52, which we know by now reduces to 1/13. But now, what if I ask you the probability that a card is drawn, that we draw a king, given that the card is a face card? So in other words, I have a standard deck of cards, and I show you, and I'm like, okay, pick a card. And you already know that that card is a face card. Like I tell you, okay, you just picked a face card. What's the probability it's a king? So I'm giving you what the first event is. Like, you know it's a face card. So now what's the probability it's a king? When I tell you it's a face card, I just narrowed down or reduced your sample space. There's no longer 52 cards in your sample space. I told you it's a face card. So how many face cards are there? There's 12, right? There's the king, queen, and jack, the face cards, 3 of them times the 4 suits. So now instead of out of 52, it's only out of 12. The way I would write this, though, is the probability of a king given the card is a face card. Okay, so I already know that this part occurred. How many face cards are there? There's 12. Now I want to find the probability that it's a king. How many kings are there? There's 4. So the probability is 4/12, which reduces to 1/3. So remember, I got this 12 from the face cards because that event, E1, that occurred first. I'm telling you, oh, you just picked a face card, and then you turn it over. Hey, what is the probability it's a king? You have a 4/12 probability or 1/3 probability that it's a king. Okay, you can pause the video and try these two on your own, and then we'll go over it together. So using the same information from the last example, determine the probability that the card drawn is a diamond. Okay, so nothing unusual about that. Diamonds are a whole suit. So there's 13 out of 52. And we know that reduces to 1/4. So you have a 1/4 chance of picking a diamond, which makes sense because there's 4 suits and diamonds are one of them. But now what if I ask you the probability that you choose a diamond given the card is a red card? So in other words, I have a standard deck of cards. I show you, like, here's these 52 cards, and I say, okay, pick one, and then I tell you, oh, you picked a red one. So now I just narrowed down or reduced your sample space. There's not 52 cards anymore. There's 26, and I got that because the red occurred first, right? It was given that it's a red card. Now, what's the probability that it's a diamond? So how many diamonds are there? There's 13 of them. So 13 out of 26 leaves you with 1/2. So the probability of obtaining a diamond, given that the card is a red card, is 1/2. In my next example, I have a family has 2 children. Assuming that boys and girls are equally likely, determine the probability that the family has 2 girls. Okay, so let's look at a tree diagram of this first. And we talked about tree diagrams in 11.4. So for the first child, right, you're either going to have a boy or a girl. And then the second child, you could also have a boy or a girl. So what would be my sample space? It's all the possible outcomes. So you could have boy, 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 girl, girl, boy, girl, girl. So we have 4 outcomes. And I want to know what's the probability of that a family has 2 girls. So 2 girls would be this outcome right there. So that's 1 out of how many outcomes? There's 4 outcomes or sample points. So the probability is going to be 1/4. Okay, now I'm looking at the probability that you get that the family has 2 girls given. So there's that word given. That means it's conditional probability. Given that at least one of the children is a girl. So remember, at least by definition means 1 or more. Okay, so this tree diagram is going to be helpful. So here I'm looking at the probability that you have 2 girls given at least one is a girl. Okay, let's look at this. So given at least one is a girl, that means that I can reduce my sample space. This is the only one where one of them's not a girl. So I'm only looking at these 3 right here. So my denominator is going to be 3. What's the probability that out of those 3 outcomes, only you get 2 girls? It's this one. So it's 1/3. And for the next one, the probability that we're going to have 2 girls, given that the older child is a girl. Okay, so I'm going to look through here, given the older child is a girl. So that would mean that it would have to be this one and this one, because it's wherever the girl showed up first, right? So your sample space is reduced down to 2 now. What's the probability that you have 2 girls? It would be 1 out of 2. So there's actually a formula that you can use, and I'll show you how you would get the answer for this one using this formula. So the formula for conditional probability, you'll want to remember this. It's the probability that the event of E2 given E1 is equal to the intersection, so the probability of E1 and E2, over the probability of E1. So it's over whatever you're given. So the given always goes in the denominator, right? That's your given. And then you always put the intersection, the and, on top. Okay, so let's look at letter B, and let's look and see how we could get the same answer. So I'm looking for the answer of 1/3, right? So here I'm looking for the probability that that the family has 2 girls, given at least one is a girl. So I'm going to use my formula. The formula just says take the 2 and make them an and. So 2 girls and at least one is a girl over the given. What's the given? That at least one is a girl. Okay, so what's the probability that you're going to have 2 girls and at least one is a girl? So let's look at our tree diagram. 2 girls and at least one of them's a girl. So that would only mean this one, right? 2 of them are girls and at least one of them's a girl. So that's 1/4 over, what's the probability that at least one is a girl? Well, these 3 have at least one that's a girl. So that would be 3 out of the total 4. So now if you remember, I showed you a shortcut for dividing fractions like this. The 4's are just going to go away, and all you're left with is the numerators. So 1/3, which is the same answer we got when we did it the other way. Okay, I know you need some more examples, so let's look at some other ones. So here's a table. It says 250 patients who had knee, hip, and heart surgery were asked whether they were satisfied or dissatisfied regarding the results of their surgery. The responses are given in the table below. If one person from the 250 patients surveyed is randomly selected, determine the probability that the person was satisfied with the results of the surgery. Okay, so let's look at this. So I want to know what's the probability that someone was satisfied. So I'm going to find the satisfied column and I'm going to go down and look at the total, which is 210. Okay, that's 210 out of how many total patients? Because not all of them were satisfied. So it's 210 over 250 patients total. So the probability here would be 210 over 250. And a shortcut for reducing, I can cancel these zeros, which is theoretically just dividing by 10. And then 21 over 25, that's as low as it goes. You can't reduce them anymore. So that would be the probability. But now, what's the probability that a person was satisfied with the results of the survey given, so here's the word given again, that means it's conditional, that the person had knee surgery. Okay, so I'm looking for probability that someone was satisfied given they had knee surgery. So I'll just call it K for knee. So the formula would be this. You're looking for the probability someone is satisfied and has knee surgery over the given, the probability that someone had knee surgery. So we're going to use our table to figure this out. So the first thing I want to look at is satisfied and knee surgery. So I'm looking at where they intersect at. So I'm going to go to knee surgery and go straight across. And I'm going to go to satisfied and go straight down. Where do they intersect at? Right there at 75. So that would be 75. And then over the probability that someone had knee surgery. Okay, how many people had knee surgery? If I go right across the knee surgery, I get 95 total people. Remember, your sample space was reduced now from 250 to just the people that had knee surgery. And of course, you can reduce this because they both end in 5. So try dividing both numbers by 5. 75 divided by 5 gives us 15. 95 divided by 5 gives us 19. Okay, try the next two on your own, and then you can unpause the video when you're ready to figure out how to do this. So we're going to still use the table from the last problem. Now we're looking for the probability that a person was dissatisfied, so I'll just call that D. given, okay, so there's my given, that's conditional probability, that the person had hip surgery. So I'll just call it H. So before I even solve it, let's write the formula. It's first going to be dissatisfied and hip surgery over the given, which is hip surgery. So now let's look and see. So dissatisfied and hip surgery. So let's get rid of this. Dissatisfied now means I'm looking at this column, and hip surgery. Where did they just intersect at? 15 over probability of hip surgery. So how many people had hip surgery? 105. That's your reduced sample space. And if you reduce 15 over 105, 15 goes into both 7 times. So it's 1/7. Okay, and for the last one, probability someone had heart surgery, given, conditional probability, that the person was dissatisfied with the results. Okay, so heart surgery, given, dissatisfied. These both look the same, but they are not. Okay, so the top part, again, is heart surgery and dissatisfied. That number's going to be a little bit different. And then we have, I should change this because the last one was heart surgery. I don't want to make this confusing for you guys, or hip surgery rather. This one's heart surgery. Let me write out the word heart so that you're not confused if I use the same letter. So for this one, I'll write it out. So it's heart and dissatisfied. Hopefully that clears it up. And then it's always over my given. My given here is dissatisfied. So heart and dissatisfied. So let's look at where they intersect. So let's get rid of this. And then let's look and see. So heart, dissatisfied. So where do they intersect at? Right here, the 5. So that's going to be 5 over, okay, how many people were dissatisfied? So that's going to be 40. And if you reduce 5 over 40, you get 1/8. So that concludes the 11.6 notes. You can start your homework for 11.6. Remember, it's okay if you need to watch additional videos for these sections. Probability can get a little tricky, and that's okay. But the more practice, the better you get at it, and the more comfortable you'll feel doing it. So please reach out to me. You can always sign up for my office hours. If you have any questions at all, please reach out and ask. I'm here to help you guys. All right, enjoy the rest of your day. Thank you.